Now let's see how we can construct the tangents from an external point exactly through the geometrical understanding or through the geometrical instruments to an accuracy to its best. So how do we construct the tangents from an external point? So let's see the construction in a stepwise process. So initially, let me assume a circle with a suitable radius and center O. So therefore, if I have a circle with center O, then I know that I can draw two tangents if I take an external point P outside the circle. The third case, as we have already discussed. So for a point P, there are two tangents which can be drawn from the external point P. Therefore, we don't know where exactly the two tangents can be drawn. I just construct using the geometrical properties. So to identify the points A and B on the circle is what is entirely about the whole construction. So how do we locate the points A and B on the circumference is the biggest question here in a successful construction of tangents from an external point. Therefore, let's take an external point P from where the two tangents have to be constructed. So here I join the points O and P using a ruler. So joining the points O and P, I get a line segment OP which is from P to O. Now I find the midpoint of PO using the bisector concept. I take the compass which is more than half and I just cut the arcs out here and this out here, and once I cut the two arcs, I join them so that the intersection will give me the midpoint of the line segment OP. So using the compass concept, taking more than half and cutting the bisectors and then joining the line of the point of intersection of the two bisectors, I get the perpendicular bisector of OP, which in turn gives me the midpoint of OP. Now once I get the midpoint, I just take the measurement of OM as the radius and draw a circle. So using the compass, I just draw a circle with as this. I draw a circle with this as the radius. Now with OM as radius, once I draw the circle, I clearly identify that this bigger circle cuts the smaller circle at 2 points A and B. The points of intersections of A and B are nothing but the located points where if I draw a line through PA will be one of the tangent for this circle with center O, and if I draw a line PB, then this will be the other tangent for the circle with center O. That is, when I take this point P and join P with A, and then I join P with B, I get the two tangents from PA and PB. Of course, PA equal to PB from the previous theorem is how I can draw the two tangents from an external point. So let's recap with once again on how we have constructed the two tangents using the geometrical properties. Initially, I take a circle with center O and I take the external point where from the external point to the center, I draw a line, which is the line segment PO. Now, once the line segment PO is considered, I locate the midpoint of PO by using the perpendicular bisector concept. We all know that we take the compass more than half and cut up and down, and that line passing through point of intersection cuts exactly in the middle of and perpendicular to OP. Now, once I locate the midpoint M, I try to take OM as radius and using a compass, I draw an entire circle passing through O and P. Obviously, it passes through P because these two distances are equal. They act as the radii for the bigger circle. So drawing the circle, I get the bigger circle which cuts the smaller circle at A and B. Now the circle which cuts at A and B are located as A and B, and then joining P and PA and PB are nothing but the required tangents for the circle with center O. So once I get the tangents PA and PB, they are nothing but exactly the two tangents which can be constructed from an external point. But the biggest question here is why? Mathematically, I want an evidence on why this bigger circle cutting at A and B exactly makes us evident that these two are the tangents is the biggest question. Maths is not about assuming, maths is about proving the results. So how do we prove that what we have taken are mathematically valid for being the tangents? Why is it that this circle cutting here makes the tangents is the biggest question for here. So let's see. Clearly, when I take the bigger circle, my radius, my diameter here is PO for the bigger circle. Now since PO is the diameter, if I just join A with O, I get this to be 90 because this acts as the semicircle for the bigger circle. Therefore, with MS center and OM as radius, I got the bigger circle where I join AO, I get triangle PAO is a right angle triangle right angled at A because angle in a semicircle is 90 degrees. Therefore, this angle will be 90. Now, indirectly, I have the radius perpendicular to tangent because angle in a semicircle is 90 degrees for this bigger circle. But if you take the smaller circle, I get the same angle to be the radius which is perpendicular to tangent. Because this angle is 90, this must be a radius and this must be a tangent to that radius. Is how we conclude using the concept of radius perpendicular to tangent. So mathematically, since the angle in a semicircle is 90 degrees, therefore that 90 degrees helps us in locating this to be the line which is perpendicular to the radius, and hence by the theorem radius perpendicular to tangent, this must be a tangent to the radius or to the circle with the radius passing through the point of contact, and hence the two tangents are PA and PB is how we conclude.